Why don't we go ahead and get started? So welcome back everybody to EE290C. So just logistically, I think hopefully everything should be pretty clear. So first sort of round of presentations, or rather I should say the round of the final presentations is going to be happening next week. So pretty much just today and Thursday is our last round of, let's say, formal lectures. As I announced last time, everyone should definitely be here basically in 2 days on Thursday. Because we'll be doing the Eta Kappa Nu course eval, so definitely want to make sure people are here for that. We'll be doing that at the end of the class, but basically I'll say that attendance is mandatory for that. And then of course attendance is also mandatory for the presentations themselves, because either you'll be giving them or I'll grade you on the questions you ask other people or something like that. Any questions or anything on either class material or project or anything like that? Yeah.
So how long are these presentations? Because last time we went overboard by a huge amount. So.
Yeah, no. So I guess the intent is to keep it within the let's say the class window. But if we go over, that I won't kill anybody. I guess so. Basically, you shouldn't plan to have more than probably, I'd say about 15 minutes. Like let's say if you were just talking through it by yourself. And then I expect it'll probably double that by the time we're done with questions and everything, but certainly you shouldn't be planning to do like a half an hour or 45-minute talk, because then obviously we won't get out of here at any reasonable time. It's a good question. Other questions on either project, class material, anything? How are people doing on the project? Anybody close to finishing? Oh, let's do it this way. How many people have some behavioral model of everything kind of locking? Okay, same group as last time, I guess. Oh, no, you guys do too? Okay, cool. All right, so unless there are sort of more questions on either project or class material or anything like that, I think we can sort of go ahead and dive back in. So last time we were finishing up talking about supply regulation. And kind of the last point at which we ended up on was talking about basically utilizing replicas of the actual load to improve the overall, basically, performance you can get at a given power consumption. And just maybe as a sort of brief reminder, sort of the whole crux of that was really had to do with the fact that if you use a replica, and in particular you intentionally don't put any decap onto that replica node, then basically beyond a certain frequency, you automatically see a larger noise signal on that replica node. And for all intents and purposes, that's as if you get extra gain off of basically trying to correct the noise that you see that's there. Okay? So the point of that was that, if we really did that, then now, instead of that power supply rejection ratio scaling only with sort of the square root of the gain bandwidth, now it scales linearly with the gain bandwidth. In other words, if you wanted to double your supply rejection, you only have to spend 2x the power in the amplifier, and not 4x the power in the amplifier. So we talked some more about sort of, what happened if you didn't really exactly know what the replica was, but basically, to sort of just wrap up on this, there's one last thing I want to mention, which is basically, when we play that trick of, in particular, we said that because you get this extra gain from the replica, ideally speaking, you'd like to take all of your feedback from there, right? Because basically, if you take any feedback from the real load itself, then kind of you're getting a smaller noise signal, or really a smaller effective gain. So you might as well take all of the feedback from that replica point where you get the most gain you possibly can get. But that's not really exactly free in the following sense, which is that if you really do this so-called replica biased regulator, where you take all of the feedback from that replica, then basically what you're doing is whatever pole you have out here on this output node really just shows up open loop in terms of your transfer function from that input voltage to that real regulated voltage. Okay? Now, there's many applications where you don't really care about the tracking bandwidth between that input voltage, or really the reference voltage, and that regulated output. But there is one particular application where you guys probably did use a supply regulated, or really a supply regulator, which was in the context of the PLL, right? So the problem is that if you try and do this in the context of the PLL, well, guess what? That regulator is really sitting in the forward path of the PLL, right? So if I now just go and use something that looks like this, where this pole shows up inside of the transfer function of the regulator, well, guess what? If that pole's at too low of a frequency, it'll screw up the whole stability of your loop, right? Or alternatively, it'll force you to drop the whole bandwidth of your loop because of the fact that you have this pole sitting there directly in the regulator, okay? So that's going to kind of motivate us to look at something, maybe going back a little bit to something more like what we had originally drawn, where we don't actually take all of the feedback from the replica, but instead we actually will take some part of the feedback from the real thing as well. Okay? And the motivation of doing that is if we take some of the feedback from the real output also, then basically now we can actually put this pole into some closed loop feedback gain and basically push it out, right? Push it out to a higher closed loop frequency. Does that kind of make sense to people, or? Okay, so the basic way we're going to do that, actually we sort of showed earlier on. And just as a terminology standpoint, this is at least what I called a replica compensated regulator. There's other maybe terms that people have called it in the past, but basically, I'll at least refer to it this way. Okay? So the idea is that, again, if this was sort of our replica path before, well, now we're actually going to reintroduce this feedback from the real output as well. Okay? And again, the whole point of doing this is just so that we can actually get sufficient bandwidth from this reference input here to the actual regulated output. Okay? So obviously, I'm not going to have as good of a power supply rejection ratio as I could have had if I didn't have to introduce this extra feedback. But I can still get a lot of the benefit from having this replica feedback in terms of I still will at least get whatever sort of portion of the gain is coming from there. Okay, so you can still sort of say the trade-off in terms of PSR versus bandwidth, it's still linear. It's just that the scale factor in front is not as good as if you took all of the feedback from here. Okay? Okay, so this is really the basic idea. This is actually exactly what I'm just going to sort of show how we do. But there's one sort of, let's say, interesting question here, which is, how are you really going to build this? Okay, so if you sort of just took this block diagram, it would kind of imply that you'd have one amplifier, you'd have another amplifier here. You have to have sort of this feedback ratio K there. You can do all of that. You could sort of build this direct block diagram. But it turns out that's probably not the most efficient way of doing things. Okay? So to sort of show something that actually turns out to be a pretty simple way of doing it, I'm just going to walk through a couple of steps to show us how we will get there, okay? In terms of really implementing this thing. So this first picture up on the top here, what I'm really sort of focusing on is how you build kind of this piece of the loop, okay? So just from, let's say, a block diagram standpoint, if we can, let me just redraw that really quickly to sort of show which piece it is that I'm going to be changing as we go along. So first I have that sort of subtraction that's happening there between the reference and the regulated voltage, right? I'm then taking that, I'm feeding it through some gain right here. And then in front of that I have basically another subtraction that's coming from that replica loop. So something that basically looks like this. Okay? So again, all I did was sort of, this piece that I've circled in red here, I've just redrawn it in kind of a more block diagram form here. Okay? Okay, well, so again, I can implement something that looks like this, and let me actually show the subtractions or the signs of everything here as well. Oh, sorry, and I missed there's a scale factor or a feedback gain K there. Okay? Yeah.
Is the sign on the second sum correct?
Oh, okay, yeah, you're right. I actually did flip it. Thank you. So that's a minus, that's a plus. That's right, thank you. But basically, what I'm going to do now is, what I'm going to be trying to do is basically get rid of some of these additional summation and subtraction blocks, but just doing everything in the current domain. Okay? Because if I do everything sort of in the current domain, then I can just short things together and that'll do all of the additions and subtractions that I want to do. Okay? So the first step to getting there is just that if I sort of look at this block diagram here, what I can basically do is I can take this forward gain here and kind of move it to be in the front. And I can take that same gain, and if I apply it in the feedback, then I basically haven't changed anything, right? So the picture associated with that is this top piece right here. Okay? So conceptually, I'm really trying to do the exact same thing, right? So I basically have a forward gain A that I apply to that Vin minus Vreg signal. And then I also have this feedback gain here, which is just K times A, that I apply to that, essentially, the replica signal. Okay? So again, I really haven't done anything, but just sort of moved around where the gains are actually sitting in this loop. Okay? Now again, the reason I did that is because now hopefully it should be more obvious that if I do something like this, then basically really all I have to do to implement this particular addition here is just build these as transconductance cells, right? So I have basically a differential transconductance here that's taking V in minus V reg, right? I have another transconductance here that's basically just feeding back from the replica voltage, okay? And again, to sort of add them up, I just do current summation. They have a shared output impedance. That sort of does this addition right here the way I want it to. Does this make sense to everybody, or? Okay, so if this makes sense, then actually the next step is really easy. Because if I just draw sort of how I actually build this, well, okay, sorry, let me take one step back. So when I actually build this, obviously I'm just going to use diff pairs and short their outputs together, right? But another thing I should notice, or I should point out, is that if I kind of look at the total GM that I'm using there, it's kind of proportional to 1 plus that feedback factor K, okay? Turns out you don't really exactly want that. If you really work through these transfer functions, you'll find the DC gain is not 1, and it sort of does some other stuff that's kind of annoying. I should say maybe even more conceptually, you'd kind of think that if I really have something that kind of looks like, these two GM cells just being added together, kind of conceptually you can just think of that as, well, maybe what I really mean is that I have a total transconductance, and I should just be sort of moving it from one side to the other, right? Kind of like we talked about with the phase interpolators, okay? So indeed, that's how you'd end up with this final actual implementation, which nicely enough is actually quite straightforward, okay? So what's really happening here is that basically all I'm really trying to do is just allocate some total percentage of both the transconductance and the bias current, either to sort of this main feedback path, which is doing feedback from the real regulated voltage, or to this sort of replica feedback path, which again, this is the one that really buys you both the stability and the improved supply noise characteristics. Does that kind of make sense to people, or? Okay, so now the whole trick here is that basically the way you'd sort of tune both sort of how stable you make this thing, because remember this is tying a local negative feedback loop that's allowing you to trade between the gain and the bandwidth of kind of that quote-unquote amplifier. So the way you do this design is you'd basically figure out what this ratio or what that K needs to be in order to get the right stability characteristics, the right bandwidth, and so on and so forth. And then from that, you're basically done, right? Because you sort of know how to build all of the rest of those components there. So does this make sense to people, or? Okay, so basically, and I should mention this was actually something that was sort of published by me. So if you're interested in kind of some more details, you can see this in JSC 2006. Okay, and indeed, you can sort of play this technique, and actually, in a lot of the links that you may run across, this has now become a fairly sort of common trick that people play inside of these supply-regulated phase lock loops. So in particular, I saw a few groups that had sort of some initial regulator designs where it looked like you may have actually had some of the problems that we've talked about. Hopefully now that we've sort of discussed this in more detail, you have a better idea of really how to build those things and still make them stable, but get the supply rejection characteristics you'd like to get. Okay? So this is actually all I wanted to say in terms of regulators. We've spent a lot of time on that, but that's kind of it in terms of regulators itself. The only other thing that I do want to mention is in this particular context of the phase lock loop, there is actually another approach that you can take. Okay? And that other approach maybe is sort of obvious when you maybe sort of look at how you built the PLL in the first place. Okay? So the whole problem we just talked about stemmed from the fact that we put this regulator basically in the forward path of the loop. Right? In other words, we took whatever output we had from our loop filter, and then it had to go through the regulator before it really made it to the VCO. So from an architectural standpoint, what would you really like to be able to do to make it so that you can use sort of something that looks a lot like this, meaning something where you don't really care about the regulator bandwidth, so you can throw as much decap as you want at that regulated supply node to make it kind of as stable as you can possibly make it. What would be really nice to do in terms of specifically in the PLL context to let you be able to use that trick? How could you do that?
Share the loop filter capacitance or something?
Share the loop filter?
Yeah.
Oh, you want to actually use the loop filter cap like for the decap or something like that? Okay, that's a clever idea. I don't exactly know how you do that, but that is actually a reasonably clever idea. That's not what I was thinking of. what's the problem? What's the problem in the first place? What was the problem statement as to why this was bad in the forward path of the loop?
It's an extra pole.
Yeah, it's an extra pole, right? Okay, so if I don't want that pole, then what do I have to do? By the way, this is like, forget about circuits. If I tell you you have a problem and you were like a 5-year-old kid, what do you say?
Get rid of the regulator.
Yeah, get rid of the regulator, or just don't do that, right? Get it out of your way, right? Don't have it in the path where it's a problem. Okay? So indeed, it turns out that's exactly actually a solution that you can take. Okay? So let's just draw sort of conceptually how you can do that. And don't worry, you will still have a regulator. It's not that I'm going to completely get rid of it. I'm just going to move it into a place where it doesn't, let's say, matter from a bandwidth standpoint. Okay? So first of all, conceptually, let's just imagine that I told you magically, somehow you knew what the reference voltage was supposed to be. Okay, and I'm going to draw that regulator as a unity gain feedback loop. It may be replica biased or something like that, but let's just pretend, right? So let's say I magically told you what the reference voltage should be, and then you just use that to sort of drive into your oscillator, or to set the supply voltage of the oscillator. Okay? Well, okay, so if I find some other way of controlling that oscillator frequency, for example, let's say by tuning some capacitance or changing some resistance or something like that, then now I can happily build my PLL. Right? I can have a charge pump, I can have a loop filter, I can have my PFD here, I could have, of course, my reference clock, some feedback clock, of course take that from the VCO, and so on and so forth. Right? Okay, and maybe there's some level shifter that I didn't draw here, but okay. So conceptually, right, what I've done now is I've pulled the regulator sort of out of the PLL feedback loop, right? So now I've conceptually said that I want to make this as much of a DC voltage as I possibly can. I just want it to be absolutely dead fixed, okay? So again, conceptually this works basically fine. The only minor issue is, how do you really know what this VREF is supposed to be? Okay, because typically, if I do this control through some other means, I usually won't have as wide of a range as I had by moving that supply voltage around. Because if I'm just tuning a cap or something like that, I can maybe only get a factor of 2 or 3x change in the cap, something like that, especially if I'm doing it with this analog type of technique like this. So I'm still probably going to want to be able to move that VREF around, based on, let's say, process and temperature and all these other things, to actually get it to be sort of in the right, let's say, nominal point for me to actually get the loop to work. So now, what do you guys think? How am I going to figure out what that is? How do I get that magic VREF?
You could hook up the loop filter output to that node and make it a low bandwidth.
And make it a what?
Make it a low bandwidth loop.
Ah, okay. So you are indeed going to make, you're basically in the right direction. But when you said low bandwidth, do you really mean low bandwidth, or do you mean something slightly different than that? And by the way, do you want to just literally take this and low pass filter it, or do you want to do something else?
Kind of rectify it, or
Rectify. Why rectify?
so you have enough range in your VCO.
Okay. So by the way, well, okay. Let's start drawing what that might look like. If you rectify it, remember, in principle, even this is supposed to be kind of stable, right? Even that node right there is supposed to be reasonably stable, because if it's moving around a lot, that implies you have lots of jitter, right? So it's supposed to be reasonably stable, but it does sort of move maybe faster than we can get things through here. What else could you maybe do to figure out what that VREF is supposed to be?
Separate paths from the very input.
Path from the very input.
Have another phase detector, and then
Okay, and then what would you do with that?
You do like a discrete changing of VREF. So if
Say
you
that again?
discretely change VREF, so you break your frequency ranges into different slots. So when you see that the loop is trying to push VCO as far as it can, like if that control voltage gets to the max range, you just flip
Okay, you're absolutely right. You could do something, sort of like what's known as, actually I have to, let's say a coarse tuning kind of thing.
Yeah.
Right, so you could indeed say, okay, well I know that I'm supposed to be in this frequency range, so this VREF is kind of a reasonable frequency range for that. That works very, very nicely with LC oscillators. With ring oscillators, that's a bit of a pain in the butt because the process variation alone usually kicks you sort of outside of any fixing any one particular VREF. Turns out, there's actually one very simple analog-ish looking, or actually it is really analog, although you could do it in the digital domain, that will actually completely alleviate us from that particular issue. Okay, so it'll quote-unquote automatically find what is the right magic VREF. So maybe I'll give you guys a hint. When this voltage here, on average, has moved up or down, what is that indicating about the frequency of the VCO? Like, what's setting that voltage? The value of that voltage on literally the loop filter output, on average.
The control voltage that you need to get the right frequency.
Yeah, it's telling you the control voltage you need to get the right frequency. Now, if I have another tuning port which has wider range than that lower tuning port, right? Why don't I just say that, hey, I want this thing to nominally be X. I don't care what it is, half a volt, 0.5 volts, whatever is magically good for me. And then why don't I use my other tuning port to ensure that this fast path is always centered at the right spot, right? In other words, if I really just look at movements of that voltage around some nominal bias that I pick, then basically anytime it's moved away from that nominal bias, I know the frequency has changed, right? So if I just integrate out those movements, then what I should actually be able to get is a magic VREF that tells you exactly what the right point to be at is. Okay, so let's actually just draw that. Okay, so what I'm actually going to do is I'm now going to have some VREF, which by the way is totally arbitrary at this point. It doesn't matter what it is. And let me actually call that something else. Let me call that V fixed, just to avoid confusion. If I just take that thing and integrate it, and then I feed that to VREF, then indeed I'll get this magic voltage. Okay, so that's kind of what I was saying. Low-pass filter is kind of conceptually the right thing you want to do. It's just that you don't really just want to low-pass filter it. What you actually want to do is just force it to some known spot. But you're only forcing it on a very, very slow time scale, right? So when I say force, that obviously means you want to add gain into that loop there, or into that path right there. Does this kind of make sense to people, or yeah?
But then that value may not be enough to actually, for the fast part to actually lock the VCO to it.
Okay, so that's a great question. So when you've done something like this, it's then really going to become a question of how big is the range of frequency tuning you get here, and how big is the range of frequency tuning you get here. So much like Stephen was saying, much like you also do with these LC kinds of oscillators, you want to make sure there's enough overlap between the quote-unquote bands, right? Now notice all of this is analog here, right? So what's going to happen is that initially, indeed, this fast thing, if it doesn't have enough range to get you to the frequency you want, it'll rail out. This integrator will start catching up, right? It'll start moving the frequency in the right direction. And then once it's sort of gotten close to the right spot, this thing will then very quickly catch up and go back away, and you'll basically stop at kind of the right magic spot. Does that make sense? Or? Now, a related implication of that is that indeed, sort of the range of tuning you can do here has to be wide enough that for all of the very fast changes, or all of, let's say, the quote-unquote reasonably fast changes, you have to be able to cover those with this, right? But typically speaking, that's not too bad, because again, if you have really, really big changes here, that implies you have a lot of jitter, right? So usually you'll sort of tune how much range you can get from this path to indeed match up with sort of the range of errors you expect to get in the first place. Yeah?
I actually have a question about the stability of this thing, because right now you actually have two loops. If this thing actually locked down, it's actually fine, but during the tracking phase, you have two loops potentially competing with each other. So
yeah, but so the beauty of this is that this loop here is very fast, right? So what's going to happen is that even during the initial lock, when let's say this is basically slewing, right? What's going to happen is as soon as this gets close enough, then as long as you've engineered it so that the relative time constants are sort of sufficiently split from each other, then basically this will very quickly notice that, okay, yeah, now I'm in the right spot. Right? And it'll just stop giving any input to this loop right here. Right? So in fact, from an overall dynamic standpoint, you're right, it's nonlinear and there's some funkiness that could happen there. But if you really engineer it so that, things are sufficiently separated from each other, this internal loop is stable enough that it'll make everything sort of work the right way. And that's why it's also sort of very critical that you're actually looking at this output to generate the error signal for this loop. Right? If you just had some other totally decoupled sort of thing there, then indeed it could keep on doing something without having this loop saying, no, okay, I'm done. I've gotten to the right point. Does that make sense? Or, by the way, we can write some math that sort of shows the same thing, but let's say intuitively, that's why this actually tends to work quite nicely. Other questions on this? Or? So just one other thing I'll mention. This was actually some work done by some people at Cadence. So the author was S. Williams, and this was at CICC in 2004. They didn't exactly do this as sort of a supply-regulated loop. There's some people later on that sort of extended it to that same idea. But indeed, this is actually becoming a more and more popular architecture because, again, it really allows you to decouple that sort of regulator bandwidth from the actual sort of characteristics of the PLL itself. So this overall allows you to get sort of the best supply rejection that you can get given a certain power you want to spend on the regulator and given a certain area you have for that decap there. Any last questions? Or? Yeah?
So is V fixed actually arbitrary or?
Okay, so it's not entirely arbitrary, right? So if this is really a normal charge pump, where do you think you want to put V fixed? Where's kind of a nice point to put it? Yeah, VDD over 2, right? Why VDD over 2? Because if you put it at VDD over 2, you know you have roughly the same amount of voltage across both the PMOS and the NMOS. It's easier to match those charge pump currents, right? All that other sort of nice stuff. You could obviously put this, somewhere else, but then just the range you can get on one side would be more, more constrained than the range on the other side, right? And okay, maybe there's some funky reason why you want to do that. But generally speaking, indeed, you just shove this at VDD over 2. Or you make this like a differential loop filter or something like that. And you put it at 0 differential, so to speak. Other questions? Or? Okay, great. So if there's no more questions on this, then let's actually go ahead and move into the next set of notes, which I think is going to be very useful for people as they're actually doing the projects. So the next thing I really wanted to be talking about today is basically how we do mixed signal verification. Now, I should sort of mention that when I say mixed signal verification, that could actually imply a very wide range of different sort of topics and a very wide range of different techniques that you might be applying. I'm mostly going to be focusing on sort of one subset of things, which is largely related to how do you find basically mistakes that you may have made, particularly really stupid mistakes that I'll tell you some more stories about in 1 second, and then actually see that some chip or something you're building really does work down the road. Okay? Again, there's lots of other sort of things that you may want and in fact need to verify, but that's mostly sort of what I'm going to be focusing on for today. And you guys laugh, but I should point out that the way I'm going to start this is by telling you real stories about chips that I either personally or indirectly have worked on, and real things that were wrong because some methodology like this was not applied. Okay? And again, these are like real chips that were taped out and measured and etc. Okay? So things that you do not want to repeat is the bottom line. Okay? So, and again, kind of the whole point of all of these is going to be that once you start doing mixed signal designs, where you've got like these high-speed links where they have a lot of feedback loops that are not just sort of purely analog and not just sort of purely digital, but actually cross the boundaries, lots and lots of really good opportunities to make mistakes. Okay? In particular, if it's person X doing the digital and person Y doing the analog, another really great way to just ensure that some mistake will happen. Okay? So again, these are all going to be real mistakes that have happened for pretty much exactly that reason. Okay? So this first one is, okay, well, that's not exactly a digital versus analog divide, but that just has more to do with the fact that anytime you build a big chip, really easy to just sort of miss some small little detail somewhere. Okay? So as an example, let's say we look at some link that you might be building. Okay, so you might have some continuous time linear equalizer. You might have some like DFE summer kind of thing. might have some, like, let's say, phase interpolator, and obviously a whole bunch of other blocks too, right? Well, usually those are all some sort of current mode logic type of circuit, right? And okay, so if any one of those is a current mode logic type of circuit, then usually it needs some bias current coming into it in the first place, right? And typically speaking, you want to put the current mirror for that bias locally inside of the block because you want to be routing the currents and not the voltages, because if you route voltages, as we talked about in 240, you have all kinds of offset and DC issues, okay? Okay, so then very, very common that you'll see that there's some global bias current block, okay? Which you'll stick somewhere, somewhere in the corner of the chip or something like that. And then you'll route out a bunch of bias currents into these different blocks you have in the chip. Okay, and usually you'll pick some standard number, like 50 microamps or 10 microamps or whatever, something like this, okay? Well, so first of all, when you do something like that, you as a designer, when you take your little block, you'll obviously make sure you've connected the bias current when you test your block, right? But then when you go and you put the whole chip together, how do you know if somebody actually connected the bias current to you? Okay, well, so because in particular, probably the only way you have to sort of check that is that somebody will take your symbol, instantiate it at a higher level, and then they'll see there's a pin missing or something like that, right? Well, okay, so fine. Let's say they even connected the pin. Well, guess what? There's actually nothing to stop it from, for example, let's say I zoom inside of this block right here, and that block assumed that it was going to be sent a current that was flowing into that block to set that reference. Well, what's to stop this block right here from also assuming that it was sending out a current? In other words, you just did this. Okay, and then you use that for the bias for the rest of your circuits in the chip, or the rest of the circuits in that particular block. Okay, so you guys laugh. This is a, let's say, fairly recent memory for some people sitting here in the room. This indeed happened. Okay? Because, hey, what's to stop it from happening? Like, somebody assumed one thing, the other person assumed the other thing. How do you know that they didn't assume opposite things? Okay? So, indeed, this is a real problem. Okay? Fortunately, this one's actually reasonably easy to fix. We'll talk more about that in 1 second, but real problem. Okay? Another problem, which is actually quite common, particularly when you start doing these, mixed signal types of feedback loops, is that somehow in crossing the domain between the digital and the analog, something got inverted somewhere. Okay? So just as an example, let's imagine that you had, some comparator that you were going to do like an offset cancellation loop on. Okay? So you could have some comparator, and then, you say, okay, well, I need to drive this thing out. It needs to be buffered. So you just throw some inverters down onto that thing. And then you draw like a box around this thing. And you say, okay, well, here's the digital output from my comparator. Here's the two analog inputs. Okay, and then maybe you even build like a DAC or something like that. So that's another, schematic you've got there. And then you take this thing over here, and you feed that into accumulator, and you feed that output into the DAC. Okay? So anybody see what's wrong with this particular picture that I've drawn here? Do I have a minor issue somewhere?
Odd number of inverters.
Yeah, I put an odd number of inverters in there, right? And okay, maybe if I was clever, then I put a bubble on the symbol, but again, who's to say that the digital guy that was writing the Verilog for that accumulator paid attention to you putting the bubble there, right? Or maybe you just made a mistake and you thought you had an even number, but you actually had an odd number because, you forgot to count like some inverter somewhere, right? Any one of these things could very easily happen, and again, I have seen happen, okay? So again, this is one of those things where if you do this and your chip comes back and you didn't have any other way around this, you can guess what happens, right? Nothing works, right? And you're very unhappy, and your advisor yells at you, and all this other kind of stuff, right? Okay, so just, because these are kind of fun, and by the way, I mention these because at least if you know about them, that's already makes it more likely for you to not repeat them. But, I'll talk some more, obviously, about how we really will try and check this. Another mistake, which, and I was not personally responsible for, but I had certainly worked on the chip that had this particular mistake, was basically flipping the order of a bus. Okay? So this actually happens specifically in the context of doing adaptation for the equalizer. Okay? So if you guys remember, you'll typically have to do some sort of deserialization, right? You don't want to be operating on 10 gigabit or whatever it is data. You want to be doing it at some lower rate. So just as an example, very common way to build, or at least a very simple way to build the deserializer, would look something sort of like this. Okay, so you might just take your full rate clock, sort of chain everything together into a shift register, and then take these outputs and feed them into another, basically, bank of flip-flops that you'd clock at the slower speed. So this might be all S clock, and these might all be the fast clock. Okay? Okay, and so then let's say that you called this, I don't know, bit 0, bit 1, bit 2, and bit 3. Okay? Now, in this picture that I've drawn here, which bit comes before the other one? Or rather, which bit is the first bit that your receiver saw out of these 4?
B3.
Yeah, B3 is the first bit, right? And B0 over here is the last bit. Well, once I've gotten that parallel thing, and I feed it into the Verilog block, who's to say that the Verilog block didn't assume that you named it the other way around, right? Who's to say that the Verilog block doesn't think that this is the first bit, and this is the last bit? Okay? Very easy, right? Very simple mistake, because they thought 0 should be before 3, but actually 3 is before 0 in this particular case, right? Well, and of course, guess what? If you do that, your adaptation will go completely bonkers, right? Yeah.
What actually almost makes this worse is in cadence. It has a default of little endian, so even if you have a symbol where pins are big endian and you just wire the two symbols together, it'll default name them little endian, and then it'll switch them on you.
Yeah, no, by the way, I mean, the specific error we had was that, the default assumption in, I believe, Simulink was different than Verilog.
Yeah, so.
Right? So, it's very, very easy for this to happen, right? Very, very easy. Okay? And in fact, it did happen. And in fact, I know of, let's say, multiple things where this happened. Okay? So, again, definitely something you want to be able to check. And again, we'll say some more about how you would check something like this. You're absolutely right. I mean, tools make all kinds of assumptions, right? And usually they're good assumptions. But as soon as you sort of cross a boundary between one set of tools or one set of things that one person is doing and another set of tools that maybe even the same person is doing, may not get the same assumption anymore. Okay? In fact, there's another very closely related sort of bug that has happened to many people that's related to this one, which is, a lot of links fairly commonly use the sort of so-called DDR clocking, or double data rate, or use both the positive and the negative edges. Okay? Well, another very, very common issue is to actually flip which one means what in a particular phase. Okay? So as an example, let's say we were building like a transmitter with equalization in it. Okay? And so let's say we did something where, this upper thing here, which let's say we clock by clock, and that bottom one, I've drawn a negative edge triggered flip-flop there, meaning that it's clocked by clock bar. So let's say I call this 1, and I call this one alpha. Okay? And then I add those two outputs together. Okay? Now, to get this to really work, I need some sort of, at least conceptually, another, let's say, mux or something like that at the output to sort of select when it is that I use that output there. Okay? Well, so notice, because I have this DDR system like this, depending upon when I look at this output over here, I could be implementing either one of the following two filters. I could either be implementing 1 plus alpha Z inverse, but guess what? I could also be building alpha plus Z inverse. Right? Because depending upon when I use that output, I will get actually the opposite filter. Right? Because in one case, I'm looking at the previous data bit, and in the other case, I'm looking at the next data bit. Okay? So, depending upon whether you clock this with clock or with clock bar, that will change which one of those two filters you actually get. Okay? And again, by the way, this happens to typically cross the sort of digital versus analog boundary, because there's some stuff you were doing over here that was all in the digital domain to kind of get that data in the first place, and then there's this other stuff you're doing over here in the analog where you made some assumption about what the right thing to do is. Right? So by the way, does anybody happen to know, do I want to use clock here or clock bar to actually look at this output if I want this filter, which maybe is the one I want? So in which phase is it that you'd actually get the previous data here versus there? Does anybody know? Yeah. So by the way, if you guys don't see that, draw the picture and you'll see what happens. Okay, so again, you have to be really careful with these kinds of things because it's very, very easy to make a mistake. And then oftentimes when you make these kinds of mistakes, they're sort of, unless you had some other, let's say, so-called chicken bit in there. And by chicken bit, I mean some way of, flipping it from what you thought it was supposed to be. You can be dead. Okay? This particular error, by the way, I don't think I wasn't ever involved in a chip that did this, but there was more than one that I know of that had this exact problem. Okay? This last one, which, okay, I think this one I never actually had a chip that made this particular mistake, but, we came very, very close, was actually sort of, let's say, different assumptions about what the representation should be. Okay? And so this one actually tends to pop up a lot in high-speed serial links, because let's just look, for example, at your typical offset cancellation DAC. Okay? So your typical offset cancellation DAC may look something like this, right? You've got some magnitude bits there, right, which are sort of controlling how big that offset current is. And then you've got a sign bit over here that selects which side should you be steering that current to, right? Okay, so in terms of binary number representations, what is this? Yeah, it's sign magnitude, or rough, depending on how you did it. If there was a differential DAC in there somewhere, you might be able to call that one's complement. Okay, but basically, it's sort of a sign magnitude representation, right? Okay, well, when you build your digital accumulator, right, which will typically look something like that, and you just throw that into Verilog, and you hit the synthesis button, what is most likely going to be the representation out there? Yeah, it's going to be 2's complement, right? So now, if you take that 2's complement signal, you just tap the upper bit off of there and then use the rest of them for that magnitude DAC, unfortunately, you will not be very happy, right? You'll get something that just does some totally bizarre thing. Okay, maybe in one half of the code space it's kind of okay, but in the other half it'll just do something weird, right? It'll kind of flip the polarity of the feedback loop, and all kinds of fun stuff will ensue. Okay? So kind of the point here, which is actually really going to be a recurring theme, is that a lot of these issues are really tied to the fact that different either designers or even different, let's say, methods of building the things can be making different assumptions. And if you never have a way of checking that those two are actually the same, you're very likely to end up with one of these mistakes. Okay? So the question, of course, for today is going to be, how do you catch these things? And how do you catch them, obviously, before you tape out the chip? Right? Which means that you're going to have to catch them basically in either simulation or some sort of other verification step that you take. Now, a lot of these, I've really said simulation here because a lot of these, they're really sort of related to a high-level behavior. Right? So it's actually kind of hard to write an explicit formal verification because that's sort of like saying you have to formally verify that the thing behaves the way you want it to. Right? Which just means, okay, you have to run sort of a behavioral simulation. Okay? So let's just walk through sort of a few different options in terms of how you might be able to find something like this. So at least for that very first error that we talked about, basically checking the DC operating point is a pretty reasonable thing to do, right? Because obviously, if I went and just ran a DC sim on this thing, I would see that, okay, that darn thing does not have any bias current, right? It's just connected to ground, so clearly something is wrong, okay? So that does indeed work. And so, I'll put yes here. You should do this. But, unfortunately, that's not always as easy as it sounds, because typically you will indeed have, a few thousand bits of sort of scan configuration and stuff like that you're going to do. And so even to get this to work, you'd have to set up all those scan bits, which can kind of be a pain in the butt. Okay? So, nonetheless, you should indeed do this. You should do this, actually, maybe even using ways that we'll talk about further in a second. But, okay, this will solve some subset of the problems at least. But obviously for, let's say, things like, inverted feedback or flipping the orders of buses or things like that, that's really tough to find with a DC sim. Okay? So for that, you're actually going to have to do something more sophisticated. You're really going to have to run sort of the entire either chip or link or whatever it is. Okay? So if that's the case, well, okay, what's the next sort of thing we can try? Well, we could just take the entire chip, netlist it, and then try and run a transient simulation for that thing. Okay, so people are laughing already, but why is this obviously, or well, besides, well, okay, I guess there's one obvious and one also obvious, but perhaps slightly more subtle reason why that doesn't work. So what are the reasons why that's sort of horribly painful?
Really slow.
Yeah, it's really slow, right? This just takes forever. Okay, now here's the question. Why does this take forever? What's the underlying reasons it takes forever? Okay, that's certainly true. You have lots of elements, right? That's definitely true. Now, that in and of itself may not necessarily kill you, but that is true. But what's the other thing that does tend to kill you?
Initial condition.
Okay, actually finding the initial condition indeed can be quite painful. Let's assume we pull a big hammer and we start the supply at 0 or something and we get around that, although that is indeed a potential problem. Anything else?
Different time scale.
There we go, it's the time scales. Okay? So just to give you an idea, let's even just look at a PLL by itself, right? So in a PLL by itself, let's just take our particular example. So I told you that you had a 500 megahertz frequency reference, right? What does that mean your loop bandwidth is? At best. Yeah, about 50 megahertz. Right? If you're really good. What's your VCO frequency at?
10 times.
Yeah, 5 to 10 of that, right? So maybe anywhere from 5 to 10 gigahertz, right? So we've already gotten, a good 2 or 3 orders of magnitude just from that, right? But oh, by the way, what was the resolution you wanted on your phase interpolators in terms of the time step? Roughly. What'd you guys do?
4 seconds.
Yeah, let's say about a picosecond or so, right? And oh, by the way, if you want to make things even more nasty, anybody do any AC coupling? What kind of time constants did they have for that?
Microseconds.
Say that again?
Microseconds.
Okay, yeah. So that was probably, in the single megahertz range or so, right? So basically, you can see very quickly you're ending up with orders and orders of magnitude difference in the timescales. Okay? Now, that's not to say that there aren't really clever simulation algorithms and things that people have come up with to try and speed these kinds of things up. But bottom line, it's always going to be slower to do huge timescale differences than it is if you just had something that was sort of relatively contained. Okay? That problem, unfortunately, is fairly fundamental, but indeed is actually one of the really big issues with this. Okay? So kind of if you sort of combine, let's say, you have a large number of elements, you have really big timescales, and oh, by the way, SPICE transistor models are complicated. Right? There's a lot of calculations SPICE has to do just to give you any kind of answer there, right? So overall, all of these combined really make this obviously basically take forever and a day. Okay? So that's not so feasible. Okay, well, so what else can we do? Well, the next sort of step up, let's say, in sophistication you could take would be you say, okay, well, I have a lot of digital stuff. So maybe for the digital stuff, I'll just use Verilog and I'll simulate that in Verilog. And I'll take those Verilog outputs and I'll use it to drive into the analog stuff. But the analog stuff I'll leave as the bare transistors. Okay, so this is a so-called mixed mode simulation or AMS simulation or, basically any one of another co-simulation, any one of a number of those other names. Okay? So this is indeed definitely an improvement. Okay, because as we'll describe in 1 second, you can definitely simulate the digital stuff much, much faster by running it in a sort of, HDL type of simulator. But still, actually, even this may not be sort of perfect. So what's the problem you still end up having here? Why can this still end up being kind of slow?
Still like continuous time versus discrete time.
Okay. And what does that imply?
The jump between an analog simulator and a digital simulator.
Okay, that's true, but why is, so presumably the analog simulator is slow, so why is the analog simulator slow?
You still have a lot of switching events and stuff.
Okay, so what you're kind of getting at is that the analog is still slow.
The RF is in the analog domain, right?
When you say RF.
The VCO and
Yeah, okay, so the oscillator is still in the analog domain. All of the sort of, signal processing stuff is still in the analog domain. Those are all still transistors, right? And still you basically have to simulate over a very long time scale with precise timing resolution, right? So you still have this sort of time scale problem, okay? And then also just, you have complex models even for very simple functions, right? Because again, if everything is a transistor, SPICE has to solve a whole series of basically, coupled linear differential equations just to find any one particular time step, right? So the next step from that would be to say, okay, well, instead of using the bare transistors, why don't I still do a mixed mode simulation, but with like a simplified Verilog A model, okay? So indeed, actually, this is now again, getting much, much better, because at least you're not dealing with all of the, horribly complicated SPICE equations. Right, now you're just maybe dealing with something much more simplified because you know what the block is supposed to be doing. Right, so again, this is good. But it still turns out to be occasionally, or in many cases, slow. Okay? And the reason for that is, again, just that, if you have this analog model that kind of is taking continuous time inputs and, basically has to simulate over all time what those continuous time inputs are doing, you still have that time scale problem. Okay? Now, we can never really completely get rid of that. You're always going to have this issue of just fundamentally you're dealing with widely varying timescales. But there is one nice thing that you can do. Okay? And the nice thing you can do, which is what sort of most of the rest of this lecture is going to be about, is actually try and do the analog modeling with a hardware description language. Okay? So when I say hardware description language, I really mean hardware, like, digital hardware description language. I do not mean Verilog A. Okay? And I don't mean, anything else that, has that A in it that's actually solving differential equations. Okay? I really mean doing it in something like Verilog or VHDL. Okay? So the key advantage of doing this is really related to runtime. Okay? And the reason why potentially if you do things right, you can actually get substantially faster runtimes is sort of twofold. One is obviously you're using the simplified models like you were going to be doing in the previous example. But more importantly, this is all event driven. Okay? So the real reason why those digital simulators are much, much faster, in many cases, is that until something actually happens, they basically ignore, they don't really do any work. Okay? So if you write your analog models to really utilize that characteristic, you can indeed substantially speed up the overall simulation time. Now, that's not to say that you can get rid of all events everywhere, because, as an example, there are things like clocks, or other of these, let's say, continuous wave types of circuits that unfortunately are continuously generating events. But again, you can actually make this thing, if you've done things right, you can get rid of a lot of the sort of, let's say, thornier circuits in terms of having to simulate them and go through the details of those models and things like that. Beyond that, there's actually some other sort of nice advantages here. So one is that, okay, maybe these days most people do indeed have Verilog A or something equivalent to it. But, if you're talking to, let's say, system company that just wants to take some big chip that you've built and use it, let's say, in their big router box, they may not really be analog people, right? They may just want to take some maybe not very simple, but some reasonably simple model of your thing and plug it into their whole big, box that's got all kinds of software running on it and all kinds of other things like that. So from that standpoint, if you've got a model that actually runs in the digital sort of, framework, it's usually much easier for them to sort of do the porting and actually utilize that model. Okay? The other piece, which is actually quite critical from the standpoint of a lot of the things that we were talking about before in terms of making mistakes, is that you're now actually going to be checking everything in one single environment. Okay? In other words, you're going to be simulating everything all in the sort of the same place. So at least from the standpoint of the assumptions that that one simulator is making, it'll at least all be consistent with itself. Right? That may not mean you get the right answer, but at least they'll be consistent with each other. Okay? Whereas if you start crossing simulator boundaries and things like that, then now you potentially have issues with, one simulator assumed one thing, another simulator assumed another thing, and you just don't get really the answers that you wanted. Okay? So that's not to say that this is the only way to do things. Actually, doing these kinds of things is also quite useful, and that's why, in class I told you guys, or in the project, told you guys build Verilog A models, or at least build some behavioral model for everything. But since not as many people have seen sort of how you do this, That's what I want to spend most of sort of the rest of today on. I should mention that a lot of this material is taken from this reference here. So this is from Carl Werner in CICC 2005. So this is him and some guys from Rambus that sort of, I think, first talked about a lot of these issues, at least in the high-speed link context. But again, this is actually a very common technique that I think you'll see in many different areas these days. And for all of the reasons we said earlier, of just really easy to make these kinds of mistakes. And so very, very common that you want to have some infrastructure in place to just make sure that they don't happen, or at least certainly the things you've seen before do not repeat themselves. Okay? Does this kind of make sense to people, or?
It's like you're putting a little bit of analog with your digital instead of the other way around.
Yeah, well, okay, so it does actually depend, there's a lot of these, let's say, questions about the context as to what's the master and what's the slave, right? Is it the analog that's a master and the digital that's a slave, or vice versa? From this standpoint, as you'll actually see in 1 second, I'm not really going to explicitly say which one is which. I'm just going to say that I want to have one of them has to be the, let's say, verification engine, right? And because the only way I can make things run in a reasonable time is do that verification in the digital domain, all of the verification should be in the digital domain. That's really kind of what I'm saying. Okay, so actually that does touch upon a point which is very important, which basically I wanted to talk about next, which is that even though we're going to be doing all the verification in that digital hardware description language, you as the analog designer, and typically in most mixed signal chips, at the end of the day, the thing you tape out, that representation is typically in cadence, right? It's typically, GDS or some, custom layout that you run LVS on the whole cadence database, okay? So because of that, if you're going to be doing the verification sort of in this hardware description, but you're actually going to be taping out something that's in cadence, it's absolutely critical that those two things are pin compatible with each other, okay? Meaning that they have really the same representation. So when I say pin compatibility, what I really mean is, just as an example, let's say I had some amplifier, right, and I look at its schematic representation. Right, let's say it's something like this. I have an IP, an IN, a VSS, a VDD, and an output over here. Then I want to make sure that that same amplifier, whatever representation I use to do the verification in that HDL, better have the exact same pins. Okay, so as an example, if I write this in Verilog, I would do module, let's say amp, out, IP, IN, VDD, VSS, right? And then I write whatever my behavioral thing is in there, and I do that. Okay? So the point here is that the way you're really going to be doing this is that given that you're really going to have this still schematic, or let's say schematic/layout database, and then the separate HDL database, what you should always be doing is still storing that HDL along with the schematic itself, and then ensuring that those two things have the same pins. And then when you want to run a verification, you'll just netlist using this view, right? When you want to run, let's say, the behavioral verification, you netlist using this view. When you want to run the layout verification, you'll netlist using the normal view that you used in the past. Okay? This kind of makes sense to everybody, or? Yeah.
So how would you do it if you want part of the analog part to be schematic, part of it to be HDL?
Okay, well, in order to do that, you have to be doing something more like this, right? You have to be doing sort of a mixed mode kind of simulation, but you could indeed do that through, for example, some configuration view or something like that,
But
right?
The interface is different. Right?
Yeah, okay, so if you have to add in, let's say, A to D and D to A converters and things like that, then, and we'll talk about this in 1 second, the way you'll usually end up handling that is you'll have to put things inside of the schematics that just sort of indicate to the schematic how the right way to deal with things under different representations is. Okay? The other thing that's actually very important about this is that given that this is the case, you should really be, let's say, very wise about how you choose the schematic boundaries. Okay? Because if you choose the boundaries in the wrong place, you can actually make it much more painful to do exactly the types of things you're asking about. For example, in one case using a full SPICE simulation, in another case using the behavioral simulation, and so on and so forth. And I'll show another example as to how sort of where you choose the schematic boundaries can directly interact with sort of how you build up these behavioral models. Okay? Okay, so that's kind of the first point. the next thing is just sort of, what's the, let's say, the very basics of how you do analog modeling in some hardware description language. Okay, so the typical way you'll do this is anything that you want to model that's an analog quantity, you'll just represent it as usually a 32-bit integer. Okay, so pretty much all of the hardware description languages support integers, both signed and unsigned. So usually that's the way you'll do it. Now, you might wonder, why did I say to do it with an integer versus with like a floating type of data, let's say either a single or double precision floating number? You can indeed do it that way too. It just turns out that in many of the hardware description languages, you can't easily pass those between different blocks, or they sort of have some annoying, let's say, implications in terms of how you use them. So for many of the systems that I've seen, they really just end up modeling all the analog stuff with 32-bit integers. Okay? So if you do that, then what you'll do is, a priori, you'll pick sort of what the unit of that integer is in terms of either voltages or currents. Okay? Because 32 bits, I mean, that's a wide dynamic range, right? That's about 2 billion or so. But still, you can actually hit that dynamic range pretty easily. Okay? So just as an example, you might say that let's say the LSB of that integer might be 1 microvolt or 1 nanoamp, and these are chosen somewhat arbitrarily. You could do it 1 nanovolt and 1 picoamp, but basically you have to sort of a priori fix what those numbers are, so that then when you do the overall simulation, everything will make sense, right? Everything will be self-consistent. Okay. The other thing which we sort of started touching upon is that you will very often have to do some sort of netlist post-processing to really get this to work the right way. Okay, so in particular, right, when I do this in my schematic representation, each one of these things, the in, the out, the in, IP, the IN, the out, all of those are sort of single wires, right? But when I model this in my hardware description language, I just said I wanted to model that as a 32-bit integer. So that would now be, unfortunately, a 32-bit bus, right, instead of actually being a single wire. Okay, so oftentimes what you'll need to do is have some sort of either directive or comment or naming convention in your schematic that says, oh, this is actually an analog wire. And so when you netlist using this behavioral HDL version, actually you should convert that to a 32-bit bus. Okay, so that nothing barfs or complains on you when you do it. Okay? The other thing which I'll mention is you'll often typically need sort of type conversions, so that you know when it is that you're going from either voltage to current or current back to voltage, right? And I'll actually show some sort of examples of that. But obviously keep in mind, whenever you do this, basically you have to sort of specify kind of what that gain, quote unquote, is. Okay? And obviously the units of that gain are either resistance or transconductance or Siemens or whatever. Okay? By the way, one sort of thing that this will touch on, which we'll see a couple of times now, is that unfortunately, when you do a circuit simulation, every node actually has sort of information about two things in it. It has both potentially a voltage, or at least a potential relative to some other fixed point, but it also actually has a current in it. And when you do things in analog HDL, no such concept, right? Every node just has one value associated with it. Okay, so we're going to see there's a few issues we're going to run into because of that. Okay? Okay, so let's just sort of take a simple example here. Okay? So maybe I'll give you guys 30 seconds or something to look at this thing and see if you guys can figure out what the simple example is actually doing. So just as sort of, a heads up, this thing right here is sort of what the instantiation would look like if you weren't doing any behavioral modeling at all, right? So that's just sort of the direct schematic pin compatible representation. And this thing down over here, that's what you'd actually use if you were doing the behavioral model. Okay, that's if you were actually simulating things in Verilog or VHDL or whatever it is to simulate what this circuit is doing. Okay? So, anybody figure out what this thing actually is? I'm assuming you guys know Verilog at this point. So what is this thing?
DFE tap.
Oh, okay. Well, you made it more sophisticated. You would indeed use something like this for a DFE tap. That's true. So, but what what's like? How many transistors is this? You're right. It is inside of a DFE tap. But how many transistors is it?
Two transistors.
It's 2 transistors. right? How are those two transistors hooked up?
That's a diff pair, right?
Yeah, it's just a diff pair, right? So all it's doing is you have a D input, you have a D bar input, you have, what do they call it? I believe I tail over here. And it just says if D is basically greater than 0, then you steer it this way. Or sorry, if D is greater than D bar, you steer it fully that way. If D is less than D bar, you steer it fully the other way. Okay, so this is basically just a diff pair. Okay, now this is actually kind of a silly diff pair in the sense that it's fully steered. Right, so it's even saying that it's really digital inputs and not analog inputs. Okay, you could obviously do something more sophisticated if you had analog inputs. But this is indeed just really a differential pair like this. Okay? So just a couple of things I want to make sure that people noticed. Notice that if I was using this directly in the sort of, in the pin compatible thing with the schematic, this out and those out bar, those would just be single wires. But notice here, now that's where I've expanded it to a 32-bit bus. Okay? Similarly with that I tail, right? In the schematic compatible version, that's just a single wire. But in the model, it's 32 bits, okay? Because it's, again, representing that analog value, okay? Make sense to people, or? Okay, so let's actually look at another example, okay? So again, I'll give you guys maybe, 20, 30 seconds, and we'll see if you can figure out, oh, yeah.
In this case, I guess, out and out bar are representing the current and not
That's
the
right, they're
voltage.
representing currents. That's right. Now, okay, so unfortunately maybe the naming convention here wasn't great, because maybe we should have called this I out and I out bar, to be clear that this is a current and not a voltage. But yes.
How did it choose not to represent D and D bar as...
Oh, because in this particular case, the thing that we're trying to model was indeed most likely something like a DFE tap or an offset cancellation where it's a digital input.
Okay. Because you could, threshold it.
Yeah, that's right. You absolutely could say that this is actually an analog input. But by the way, this touches, what this gets at is that you should write the behavioral model for the way this thing is going to be used. Right? If you know it's going to be used with a digital input, might as well write the behavioral model with that type of input.
So then there's some markup that tells it not to...
Yeah, so in the schematic itself, there would have to be something that says this is an analog input versus this is a digital input. Right? So indeed, you'd have to have some way of telling it what should be treated which way. And that could either be with a naming convention, it could be with some, let's say, quote-unquote comment you put in the schematic that the post-processing uses. There's a bunch of different ways you could solve that.
Quick question.
Yeah.
Why do you multiply by I bias equals I tail times 4 there? What's
Here, you mean?
I
Oh, okay.
bias.
So in this particular example, there's actually a bias current being fed into it.
Oh.
And so actually in this particular example, I should be totally fair, there's a couple more transistors because there's actually sort of implicitly a current mirror there.
Oh, I see.
Right, so implicitly there's actually something like that inside of it, where there's a 1-to-4 ratio there. Yeah, that's right. Okay?
Shouldn't it be the other way around?
Yeah, it's the other way around.
I bias should be the other one and I tail should be.
Oh, I bias. Oh, I'm sorry. Okay. You're right. This is called I tail, and that's I bias. Good. Paying attention. Okay, so in that case, what is this doing?
Current DAC?
Say that again?
It's a current DAC.
Yeah, exactly. This is a current DAC. All right? Because all it's really doing is taking some basically, nominal, let's say, I master bias, which is just some master bias current, and then based on the digital bits, multiplying that bias current to the output. Okay? Now, there's one interesting question here, which is, why did I write the DAC, the whole DAC like this, versus, as an example, taking each of the subunits of the DAC and modeling it this way? Anybody know why you might actually want to write things this way versus just modeling each subunit and then letting the thing put it all together afterwards?
I have to write it again.
Hmm?
You don't have to write it again. If you have 16 tabs, you write current DAC 16 times.
Actually, no. So unfortunately, it's the reverse way because if I use this one model for one of my unit cells, then if life was good. And I'll explain the reason why it's not good in 1 second. But if life was good, then I would just write the model for those unit cells. And then magically everything should work when I put it together, right? I wouldn't have to write any further models after that. So what's the bad news? Why does that not exactly work?
Is it because you're using like if
Converse.
conditions out here, so the continuity is a problem?
Sorry, I'll Shiva, go ahead.
Okay. Is it because you're using if conditions out here, so the continuity is a problem? I mean.
Oh, I think I actually ensured that it was always driven. So that you see how there's a greater than or equal or a greater here? So I think I ensured that it's always driven. You're right that maybe the simulator isn't the most happy about this, but actually Verilog is kind of okay at dealing with these kinds of things. The real issue actually has to do with what Chintan was saying, which maybe was what Linkai is going to say.
Oh, I was going to say when you show them the current ends get together.
Ah, there we go. Okay, so the real problem is, remember I said before that, Spectre or Spice, every node has 2 values associated with it, but in Verilog there's only 1, or VHDL there's only 1, right? So let's see specifically what would happen if I tried to build the DAC the way I proposed. Okay? So let's say in my schematic, I do something like the following. Okay, so I have my schematic for the top level DAC, right? So let's say I do something like I put a resistive load, and then I have these like little, current units that are basically turned on by the digital bits, right? And I just connect them together like this. So I have like, a DAC unit 0, let's say a DAC unit 1, and so on and so forth. Okay? So that's like my DAC schematic, right? And then if I look inside of those, DAC unit schematics, that, let's just say, looks something like this, right? So I have some V bias here and some digital input, right? And that's, let's say, my output right there. Okay? All right, well, so now let's say that I go and I write a behavioral description for that. So I have my module, DAC unit. It's got, let's say, I out. Let me call that I out. Let's say D and V bias. Okay? And I write whatever that is, which of course will just be basically some switched current source. Okay, well, so now when I make this netlist, what Verilog is going to try and do is instantiate, and in particular, obviously, there's going to be some output here, which will be I out. Right? What Verilog is going to try and do is put basically, DU0, let's say, with its I out driving one particular node, and let's say that's D0, and let's say that's V bias. And then it's going to have a DU1, and it's also going to be tied to I out, and it's going to be D1 and VB, right? Well, so now what you're basically doing is those two modules are going to be fighting with each other, right? So if you actually try and simulate this, the thing will come back and barf on you and say, sorry, I can't simulate this, you have a drive fight, right? I don't know what it is that you really wanted there, okay? And again, the issue really comes down to the fact that what you really wanted to have happen was to have these two currents sum at that node and become a voltage, right? But because Verilog or VHDL doesn't know anything about those semantics, it's just going to take whatever signal you use to represent, the current from one and the current from the other, and then just try and drive them onto the same node, right? Which clearly doesn't work. Okay? So one way indeed that you could solve that is you say, well, okay, I'm just not going to build the model for that. Instead, I'm going to build the model for this. Okay, I'll just build the model for the whole DAC, and then I sort of don't have to worry about this particular issue. Why is that kind of potentially bad, by the way? Why is it that you may not want to build the model for the whole DAC like this?
Not representing what's actually on your chip.
Ah, okay, there we go. So there's one issue which is, related to maybe what we were saying before was, okay, it takes me more work because I have to write the model for the whole DAC. But the more important issue is the higher level you go, the more likely it is that the model you wrote does not represent the real hardware, right? Because the higher level you go, the more likely it is that there's some minor detail, quote unquote, that you had neglected somewhere that does not actually match with what's really in the chip. Okay? So to the extent that you can, you really do want to write things sort of as low of a level as you can to make sure that you avoid a lot of these issues. Okay? Now, turns out there is actually another way that you can fix this particular problem, although it does involve, again, sort of some custom post-processing that you'd have to do. So the way you could fix that problem would basically be to say, okay, whenever I build my schematic, I'll still sort of have these individual DAC units. Okay, so let's say DU0, DU1, right? But then what I'll do is, instead of just directly connecting them together, I'll build this sort of box thing that will indicate to my behavioral model that actually you're supposed to sum those two together. Okay? And then what you do is inside of this little box that I drew here, for its schematic representation, since you know that Spectre or Spice or whatever it is will perfectly be happy to just short those things together, in the schematic for that symbol, you just put, 0 volt voltage sources, right? Or 0 ohm resistors, whatever essentially your LVS will ignore or just treat as being a short, right? So you'd call this, let's say, out, 1, and 2. Okay, and then obviously in your HDL, that's where you'd say that out is equal to 1 plus 2. Okay? Does this kind of make sense to people, or? Okay, now obviously the annoyance of this is that now you'll have to write something that goes and does the post-processing, so it finds all these things, and then, at least for the HDL, uses this, or rather I should say, not the post-processing, you have to build these boxes in the first place, right? So when you build your schematic, you have to put those boxes in, because you know that the behavioral model will have a problem if you don't put them in. Right? So it's a little bit annoying, especially if you have a really big current summation that you're doing. But, again, that's still sort of a reasonably workable solution. Question, or? Yeah?
Why don't you model your resistor as a 2 input and 1 output instead?
Okay, so in some senses you could indeed do that. Although, actually, even for the resistor itself, if you kind of think carefully about it, even the resistor itself, I still actually have a problem, right? Because the units of this out right here are current. But the unit of that out right there is voltage, right? So if you actually think more carefully about the resistor, the way you'd actually build the model for the resistor is actually something that would most likely have 3 terminals. It would probably have at least the resistor that you know you're going to be using for the purpose of converting to voltage. You'd have an I in, and then you'd basically have, maybe a V out plus and a V out minus or something like that.
I'm just saying you have, like, in this case, you have I in 1 and I in 2, and then you have a V out.
Right, no, I guess, so you were just saying that basically instead of writing this for that one resistor, I would just have an I in 1, I in 2, I in 3, I in 4. You absolutely could do that, right? The only annoyance would be that for every resistor you have, you'd need a different sort of number of inputs. But okay, I mean, maybe you could then argue that you need a different number of these summer inputs in general, although I guess I could build a tree of these and add them all together or something like that. But
I'm just saying, in the real layout, right, you can also review that as multiple input, because in the real layout you have parasitic resistors from that one terminal to the other part.
Oh, you're just saying put a resistor in between all of these, or?
That's right.
Yeah, but so even if you put a resistor in between, when you add that resistor in, what's your behavioral model for the resistor?
No, I'm just saying that if you look at the number of things, you will get multiple inputs in the layout level. Just because of the fact that you're actually taking different inputs at a different pace.
Okay.
Right. I'm just saying that's more close to the layout.
Right, but I guess, I mean, isn't this box doing the same thing?
Yeah, right. It's the same thing. But I'm just saying that's a little bit easier to model in schematic.
You mean just so again, just to make sure I'm clear, you mean putting resistors in series with each of these things? Or? Because I think that's basically what this is doing. I mean, you can replace this with resistors instead of 0 volt voltage sources. It's just that this whole box I need to replace with this, right? If I just put resistors in, then I again have this issue of shorting a single node and not knowing that that shorted single node is actually supposed to be doing current summation.
Yeah, I guess that's the same.
You see the problem, or? Yeah.
I guess the real annoyance is that you have to do all of this by hand.
Yeah, well, so when you're building the schematic in the first place, indeed you have to do this by hand. Now, because of that, there is the other way around, which basically just says, if you do this, then try to draw the schematic boundaries only around voltage. Right? Because if you draw your schematic boundaries only around the voltage signals, then you'll sort of implicitly avoid that. Now, the problem there is that, again, obviously, there are a lot of structures where you'd really like to do this, right? So, for example, like in your DFE or something like that, you really will typically have lots and lots of these current sources that you really just want to sum together. So if you draw the boundary around that whole unit, then what you'll unfortunately have to do is write some long piece of behavioral code that has, D0 times, H0 times I0 plus D1 times I2 and so on and so forth, right? which is not the end of the world, but again, just means that you're probably more likely to make a mistake. Okay? So it's sort of pick your poison in some sense. You know, pick the poison of writing a more complicated behavioral model, or pick the poison of writing or of drawing this, you know, annoying schematic thing. And I think actually, I mean, I guess I'm not too biased in one direction or the other, but I would kind of say that if I knew that I was going to do this in the first place, I would probably prefer to do this, just because then I can write a very simple behavioral model, and I kind of trust that I trust a little bit more that my behavioral model at each subcomponent level is actually correct. I completely agree this is annoying, don't get me wrong, but you know, if I have to pick one annoyance, then I think maybe this annoyance is a little bit, you know, better. Other questions on this, or? Okay, so maybe just one final example, not that it's actually particularly difficult. We'll probably wrap this up next time, but just in case you were wondering, you can indeed do things like phase interpolators or delay lines and things like that in these hardware description languages as well. In this particular example, this is just showing sort of something that basically just gives you a variable delay based on a sort of bit code that's being fed to it. Don't necessarily have to do things this way, particularly for the phase interpolator. You know, a slightly different model may actually work reasonably well. But indeed, you can handle sort of time domain or variable time delays in this sort of hardware description kind of language as well. And this obviously is quite useful when you're trying to do things like, you know, checking that the CDR locks, that the VCO locks, and so on and so forth. Yeah?
You actually typed out 64 lines inside that case.
Oh, okay. So, I mean, the way this one is written, they probably indeed would do that. You don't necessarily have to do it that way, but, you know, in this particular case, yes.
Script in MATLAB to generate that.
Yeah, exactly. You can, you know, all of these things are very amenable to various types of scripting things where you figure out what it is you're really trying to do and you can replace this. Now, by the way, I should mention there are actually, let's say, very good behavioral models, particularly for voltage-controlled oscillators, that you can actually plug directly into Verilog. That will actually even capture some of the nonlinear effects. So these are things called PPV macro models. I'm actually not the expert on that, but you know, John over here is. So you know, or not is, but you know, at least knows how to use it. So if you guys are interested, come bug him. But you know, that's another, let's say, good thing to know about. Okay, so we're out of time for today. We'll pick back up. Actually, we'll really wrap up next time. So I'll see you guys all then.